So again, let me talk about the star of a mass capital A. Now, in order to understand this star in the entire course, we have considered certain models. Can you tell me what those models were? The most basic model. What did we do? This I discussed in your second semester. It was the constant density model. What did we do? We assumed that rho, which is normally a function of radius r, is just constant, say rho 0. And then using the equation of hydrostatic equilibrium, you get pressure as a function of, but this r will not be there. Still you will get a function of r, because in the hydrostatic equilibrium equation there is a r dependent. Okay, this thing I have maybe I have solved this in your second semester.
No, sir, third semester mid 7 again.
So this was constant density model. Next, you can do a little bit better than this. What we have is called linear density model. Linear density model. What do we do now? Next, what we assume is like this: rho 0 1 minus small r by capital R. Linear density model. Fine. Next, there is yet another model which is much more popular. It's called quadratic model. Quadratic density model. There we use this square. And now comes the more or less somewhat realistic model. That is a little bit non-linear model, but it is very much used, and that is what you do is just put an n over there. So the whole thing to the power n. So if we assume n is equal to 0, we get back to this model, constant density model. N is equal to 1, we have quadratic model. N is equal to 2, we have different models. Okay, experimentally to find or to match with the experimental data, this is one of the ways to attack this problem. This is a very interesting model. I have not solved these things. I have just done this in the second semester, and probably in 5th or 6th class I have talked to you. I have solved the linear density model. Okay, now these are basically very simple models. What is the moral of the story? Moral of the story is we assume some sort of dependence, or we use the density and then model the star using only the equation of hydrostatic equilibrium and sometimes the mass conservation equation. Now there are some other models also. One is the polytropic model that I have discussed to you. Remember what happens in the polytropic model? P is proportional to rho to the power gamma, right? And this such relationships has been seen for white dwarfs, and there are many other scenarios also. Polytropic equation of state we have. So basically we have a polytropic stars which obey this polytropic relationship. Another very simple model was the homologous stellar model that I discussed in my last lecture, right? Homologous model. There, using the homologous model, we found the luminosity temperature, luminosity mass dependence. Remember what was the relationship between luminosity and temperature? Approximately L proportional to T effective to the power 6. Now that thing has been observed experimentally in the HR diagram also for the main sequence stars. Okay, so this thing, homologous stellar model, is also very powerful model. All these models that I am talking about, this is the most simple picture. Okay, now let me talk about something different. This whole discussion, I am talking about non-relativistic objects, right? Non-relativistic treatment. Now, what will happen if I do the relativistic treatment? The first question which arises is, why do we need the relativistic treatment? So today I will do one problem for you for the neutron star.
Different model
There are so many issues. God did not grace us with a single model which will solve all the issues. And so, as a puny, tiny human being, we try to achieve success in different parts of the observations through different models. You can think of it like that. Now, homologous Taylor model. Now, relativistic models. অনেক রকম রিলেশন আছে ওইখানে অ্যাডিয়াবেটিক আইসোথার্মাল n ইজ ইকুয়াল টু ইনফিনিটিতে আইসোথার্মাল স্ফিয়ার হয়ে যাবে ওই জিনিসটা আই এম নট গোয়িং টু দ্য ডিটেলস রাইট নাও বিকজ হোয়াট এভার পলিট্রপিক মডেল ইজ নট অনলি অ্যাপ্লিকেবল অনলি টু স্টার্স ইট ক্যান বি ইউজ টু মডেল প্ল্যানেটস অলসো the structure of the earth also. Okay, it can be used to planet there. So it's a very general concept, polytropic model. Now let me talk about the relativistic model. What is the simplest model here? This one, the constant density model. Now what you can do, this I did the calculation in the last semester, in the previous batch. What you can do, you can solve, this is the non-relativistic hydrostatic equation. Today I will discuss about the relativistic hydrostatic equation, which is also known as Tolman-Oppenheimer equation. There, if we use the relativistic hydrostatic equation and again the constant density model, it is possible to get an idea about the Schwarzschild radius. Okay?
relativistic approach and
So it is a very beautiful thing. You see, there are so many models. This is the most simplest of them all, and using just the relativistic hydrostatic equation, it is possible to get an idea about the maximum mass of neutron star and also to get a rough estimate of the Schwarzschild radius, which is basically the radius of a static black hole. Okay, questions?